Okay. Yeah. Before we begin, I want to do a little bit of an advertisement. This is my book, which is got published quite recently. Currently, I think it shows unavailable on Amazon for some reason. I think that'll probably be fixed soon. But it's a book on combinatorics, which is similar to many of the topics I've also taught in these OMC classes. And I think the main thing which I really like about this, apart from the fact that I've written it, is that it's quite conversational in terms of, I think it's a lot like a lecture would be where I'm trying to motivate things a lot more than at least, the way I felt. I felt that when I was studying combinatorics for the first time, things may not have been as motivated towards me. So, yeah, I think if you yeah, it's currently out of stock. So I'm trying to fix that as well. Like I'm trying to figure out with people. But I think that's not a long-term issue because it'll get fixed. But
Please take the class very basic.
yeah, okay. We'll start quite basic, but we will end up covering a little bit of this thing. But yeah, beyond the point, I don't think there'll be
I
much.
do not have any idea
Don't worry.
for this
Don't worry. We'll
topic.
start from scratch. Don't worry. Okay. So I'll start sharing. Yeah. So invariants and monovariants. So this is, I think, one of the more famous, combinatorics topics. So if you've heard of permutations and combinations, etc., the first thing you probably would have learned after that is either going to be like pigeonhole principle or something like this. Um, the general quote which I like to use for problems which use, oh, I shouldn't write in white ink. Oh no, what is this? Wait, this thing is copying. Okay, yeah. So the general code, which is this is really thick, is that when too much is changing, look for what doesn't change. So the funny thing is, okay, this is like you can think of it as like a philosophical quote as well. Like, you know, if things are like changing around you, but there's some friends of yours who like are not changing, then that means that they're probably the ones you should trust. But okay, this is math class. This is not philosophy. So what I mean to say here is that a lot of times you have these sorts of combinatorics problems where they give you some sort of starting point and they allow you to keep changing that sort of starting point based on a certain tool. So it's like, for example, you start with a list of numbers, and let's say you can choose any two numbers and add them up and replace that number. So, for example, let's say I pick 1 and 3. I can remove 1 and 3 and I can replace it with 1 plus 3, that is 4. So now it looks like 2, 4, 4. And I can do it with these. So I get 6, 4. And I like this. So of course, there are a lot of different possibilities. I didn't have to start with 1 and 3. I could have started with 1 and 4. I could have started with 2 and 3, etc. But therefore, there's a lot of confusion as to, how many things can happen here, etc. But we don't really care about how many things can happen. We're looking for something that doesn't change. Um, so in particular here, something that won't change is the sum of all numbers, because at the start, the sum of all numbers is 1 plus 2 plus 3 plus 4, which is 10. And after each step, you'll notice that it's still 10. And that's quite direct because I mean, all we did is we took two numbers, removed them, and replaced it with the sum. So what we did is if you had some numbers A, B, and other stuff, we replaced it with A plus B and the same other stuff. So the sum of all numbers should not change, which makes sense. Um, and why this is useful is that even though there are so many different things that could have happened, like you can start by adding 1 and 3, or you can start by adding 1 and 4, or 2 and 3, then the next step, there's so many possibilities, etc. What this says is that eventually, when you get to the stage where there's only one number left, that has to be 10 because the sum of numbers doesn't change. Okay, also, yeah, there's some messages on chat. Apparently, people are still joining. But I think it's okay. Now that I've started, I might as well go on. Yeah. Uh, But yeah, if anyone is joining late and like is confused about what's going on, like feel free to stop me. I'll explain again. Um, so let's actually do this from scratch, right? So let's take a simple example. Again, this is really thick. Um, you have, let's say, 1, 2, 3, 4, 5 written on a board. And what you're allowed to do is pick two numbers, A and B, that are written, and replace them with, um, let's say, X and A plus B minus X. This is a pretty simple example. So if this is going like a little too easy, just have a little bit of patience. But and you want to check. So the question is, can I reach, let's say, first question is 1, 2, 3, 4, which is funnily no. And the second question is, can you reach 2, 3, 4, 5, 6? And yeah, this is quite direct because like the point is that each time I'm taking two numbers and replacing them with two numbers. So the number of numbers that are on the board, there are five numbers at the start, 1, 2, 3, 4, and 5. Now you can pick two of them and do some operation on them. So X is, by the way, your choice. You can choose whatever X, negative, real, whatever. It doesn't matter. So like for example, I can choose 3 and 4, and let's say I choose X as 2. So I can replace 3 and 4 with 2 and 3 plus 4 minus 2, which is 5. So I can remove these two numbers and I can put 2 and 5 instead. And then I can repeat this as long as I want until hopefully I reach one of these two. Now, the thing in invariants and monovariants is usually you're going to say answer is no, you can't reach. And you're going to give a proof on why you can't reach. If numbers repeat them, we write them once. No, we still write them twice. So if numbers repeat, like 2 and 2 will be written twice. And therefore, like the number of numbers won't change. Like you took two numbers and you replaced them with two numbers. So you'll always have five numbers on the board. So this is already no. Like you can't ever go from five numbers on the board to four numbers on the board if you're never changing the number of numbers on the board. But the second one is slightly more non-trivial, although it's still quite direct. The point is, again, we consider the sum of all numbers, which is at the start, it's going to be A plus B plus other stuff. And later also, it's going to be X plus A plus B minus X. And this cancels. So it's still A plus B, which was what we had here, plus the same other stuff, because that didn't change. So the sum of all numbers won't change. And so you can never go from 1, 2, 3, 4, 5 to 2, 3, 4, 5, 6 because the sum of numbers here is just larger, right? Like sum of your numbers here is what? 20, and here it is 15, I think. Yeah. So you can never go from this stage to this stage. So this is a pretty basic idea. And the whole idea is going to be look for a quantity um, that doesn't change. So here in particular, the first quantity we found that doesn't change is the number of numbers. So, okay, I'll just write number of numbers because we took two numbers and we replaced them with two numbers. The second quantity we found is the sum of all numbers. So in general, you could have a lot of other things that don't change. You could have possibly the sum of squares of all numbers, or you could have the product of all numbers, or you could have uh, the number of numbers divisible by 3, anything, right? We don't know. But the point is that, okay, you'll get this quantity that doesn't change when you apply your process. And you see how that quantity looks at the start and how the quantity looks at the end. And hopefully, these two things will not be. So at the start, the quantity will be something like 7, and at the end, it will be something like 8. And because the quantity never changed, like it's not possible because if it was 7 at the start, it should be 7 at the end. It can't be 8. That's the basic idea. So for any five numbers having sum 10, is it guaranteed that I can obtain those numbers? That's an interesting question. And the answer is yes, you can. And we'll not really go into the proof that would come more into an algorithms class, but it's not actually that hard because the point is that you can, if you have 1, 2, 3, 4, 5, and you fix your first four numbers as whatever you want, and the last as like 10 minus the sum of those four numbers, so that the sum becomes 10. The point is, because you have this freedom of x here, I can use that to manually fix these four numbers, and it'll work out. I'm not going into details, but that's like the basic idea. I don't want to like go off topic too much, but that's like just the starting point. So that was a basic example. Let's look at something slightly more non-trivial. I should not use weighting. So you have, let's say, this new question, which is that you have a lot of plus and minus signs on the board. Also, till now, is everything clear? Like, if anyone has any questions, please feel free to ask. I'll stop here for a bit. Like, does anyone have any questions? Like, feel free to like talk or message on chat, like, however you prefer.
No, we don't have any question.
What is
Okay.
invariance?
Sorry? I can't hear. Is it a problem on my end, or I don't think so, because I could
What
hear.
is the invariance?
Yo, is my net bad or is the voice breaking? Can someone please confirm?
I think the voice is breaking.
Okay, cool. So you can send your message on chat if you want. I'll answer it there. So you have, okay, so meanwhile, I'll move on to question 2. So you have a lot of plus and minus signs written on the board. And okay, maybe, okay, it's fine. So, and the problem here is basically going to be that you can choose any two signs you like. So let's say I choose plus and plus. And if they're the same sign, I replace them with plus. And if they're opposite signs, so if you choose a minus and a plus, then you erase these two and you replace it with a minus. So here you would replace these two with just a single plus. Here you would replace these with a single minus. And the point is that the number of numbers is going to keep reducing by 1. So eventually there'll be just one number left. And the question is, what is that one? What is invariance? Invariance is more of like a topic name. Invariant is what you will be looking at. Invariant is a quantity that doesn't change. Like, for example, the sum of all numbers. That's an invariant in under some processes. That makes sense. Invariance is like the kind of concept of using invariants in some sense. So yeah, like here, this problem, you're constantly reducing the number of signs until there's only one sign left. And the question is it going to be a plus sign or a minus sign? Minus. I mean, I haven't written down the full thing. Like, I just put dot 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 here. 1 second. I'll just put this. And yes, I see Athar has raised his hand, so you can go ahead.
You can replace all the pluses with, let's say, a +1 and all the minuses with a -1. And you can notice that the product of all numbers in the set is invariant. So
Exactly.
then, if the original product is +1, then we end with a +1. Otherwise, with a -1.
Yeah. So the cool idea is that you think of plus as +1 and minus as -1. So when you're multiplying things, it's like literally this, like two things that are same sign, they go to plus. Two things of opposite sign, they go to -1. So you're basically one by one multiplying all of these numbers. And because the product of all numbers is an invariant, because at each step, you're choosing two numbers and multiplying them. So let's say you had +1 and -1. You replace this with a -1. And you had other stuff and the same other stuff. The product of numbers has not changed. So you can just evaluate the product of numbers at the start. So here, for example, it would be +1. So you know that the final answer has to be +1, and in particular, it has to be a plus sign. Cool. There are other ways of thinking about this, which is that you can look at the number of minus signs. So how does so how does the number of signs change at each step? So let's say I took two pluses and replaced it with a single plus. So if I note down number of plus and number of minus. So how much is the delta? Like how much did it change by? So here it reduced by 1. Like number of pluses reduced by 1, but number of minuses didn't change because we didn't do anything to a minus. If there are 2 minuses which you replace by a plus, then plus increases by 1 and number of minuses reduces by 2. If you have a plus and a minus and you replace this with a minus, and the other case is symmetric, but we'll just do that anyway. Here, the number of pluses reduces by 1. And here also it reduces by 1. And the number of minuses doesn't change because there was 1 minus at the start and 1 minus at the end. So the point is that the number of minuses either stays the same or changes by 2. And that leads to this cool idea of actually, like ideally, in an ideal world, it would have been great if, this minus 2 didn't exist and this was also 0. Like that would have been great because then you can say that the number of minus signs is an invariant. But unfortunately, that's not true. And of course, it's not true. But what you can say is that if you look at the parity, which is whether the number is odd or even. So let's say the number of minus signs at the start was even. Then each time it reduces by 2. So an even number, when you subtract 2, it'll still say even. If you don't change it, of course, it'll still say even. So the parity is never going to change. If you had started at odd, then it'll stay odd because odd minus 2 is still odd. Like 7 minus 2 is 5. That's still an odd number. Of course, the product solution is much cooler, and that is what I would say in general is the preferred approach here. But why I am showing this is because there are a lot of problems where you try to like list down all the information that you have, like what all are the possibilities and how do things change. And things are working, kind of nice, but then you get this sort of problem, right? So how do you deal with this? You basically, in some sense, need 0 to be equal to minus 2. Then life would be great. And when is 0 equal to minus 2? When you're looking modulo 2. So I'll define this term modulo for people who are not very familiar, although I think Pranav took a class on modular arithmetic. Also, give me a second because I think someone's outside. Okay, yeah, I am back. Some messages on chat, number of minuses even. Can you show the question once? I was disconnected. The question was that you have a lot of plus and minus signs, and at each step you replace, if there are 2 things of the same sign, you replace it with a plus. If they're opposite signs, you replace with minus. And the cool slick solution is that you think of a plus as a +1, minus as a -1. Then the product is invariant because -1 into -1 is +1, etc. All of these work out. So you can just evaluate the product of all numbers at the start, and when there's only one number left, it has to be that. So, but what I'm showing now is that you can look in this modulo sense. So modulo arithmetic is basically going to say something like A is congruent to B modulo M. This means that A minus B is divisible by M. Now, for most of this class, M will usually be like 2 or 3 or some simple number. And what this is basically saying is that A and B leave the same remainder when they're divided by M. So for example, 2 odd numbers are congruent mod 2 because 5 and 3 both leave remainder 1 when divided by 2. 6 and 4 both leave remainder 0 when divided by 2, etc. And this is a pretty useful thing because, when you list down information like this and you get something like 0 and -2 and stuff. In fact, even here, right, you need -1 and +1 to be the same, which of course doesn't make sense in the normal world. But when you start looking at it in modular arithmetic sense, then you realize that when you look modulo 2 again, +1 is the same as -1 because both of them leave remainder 1. And okay, if you want to be more clear about that, it's like saying 1 minus -1 is divisible by 2. That's what we said. A minus B is divisible by 2 or M. So what you're saying is that the number of plus signs also flips parity every time. So if it was odd, it becomes even. If it was even, it becomes odd. So that's another approach to think about this problem. But we'll see some problems where, you have to do something like this because, of course, here it's a little bit of an overkill. So let's see this problem where you have three numbers with you, A, B, and C. And the allowed move is that you can change A, B, C to A minus 1, B minus 1, C plus 1, or A plus A minus 1, B plus 1, C minus 1, or A plus 1, B minus 1, C minus 1. So the point is, like, one of them you will increase by 1 and the other two you will decrease by 1. And you start at, let's say, 1, 2, 3. You want to find out whether you can reach 0, 0, 0. So just to repeat, one of the three numbers will be increased by 1, the other two will be decreased by 1. And you want to go from 1 to 3 to 0, 0, 0. And like with every problem in this class, we will show that, no, this is not possible. And to prove that, we'll create some invariant, which is different at the start and different at the end. And
Sir, can I tell my solution?
Sorry?
Can I tell my solution?
Tell me solution for this problem, the one I just
Yeah,
gave.
yeah.
We'll discuss it, but first I was more hoping that people will give their ideas.
Okay.
I think ABC must be distinct.
I think your voice is breaking. I was trying to speak.
ABC must be distinct.
I think it'll be better if you message on chat. Wait, can you guys see the screen? Screen is black. Is that for
Screen is
everyone?
visible to me.
Now it's
Okay.
visible.
Okay. That's fine.
Visible.
Yeah. So does anyone have any ideas on how we can solve this problem?
Yes.
ABC are distinct. I mean, I told you what ABC are. ABC are 1, 2, 3 at the start. They don't have to be distinct. It's like you can make them the same at some point. It's all right. So for example, a move that's valid here is you can increase this by 1 while reducing these two. So you can make this 2, 1, 2. And 2 and 2 can be different. That's all right. Yes, the parity changes every time. So the way I like to think about this actually is that there are a lot of times when you're dealing with something like there's some plus signs and some minus signs, but the number is the same. So you're dealing with something like plus minus 1 or plus minus k in general. And this is what I like to think of as, it's not really a trick, but let's say a plus minus trick, which is that whenever you have a plus sign and a minus sign and there's a lot of confusion on which one you're using, try to think of it modular 2. And the advantage of that is that plus a is always congruent to minus a mod 2. And the reason for this is that a minus minus a, which is 2a, is divisible by 2. And the point, therefore, is that plus 1 and minus 1 are the same when you look at this mod 2. So if I think of this entire thing just modular 2, so I replace like 5, 6, 7 with just like 5 is 1 mod 2, 6 is 0 mod 2, 7 is 1 mod 2. So I'll replace with this like this, if that makes sense to people. Like 5 is odd, so it's 1. Like you can think of this in terms of odd and even, but I'm purposely choosing to think of it in terms of mod 2 because when you're not working mod 2, if you're working, let's say, mod 3, then you can't say odd even, right? Like then you have to think in terms of remainders. So it's just a little bit cleaner in that sense. Some reduces by 1 each time. That is also true, but that is unfortunately not something that directly solves the problem because we had to show that 1, 2, 3, we can't reach 0, 0, 0. And if the sum does keep reducing, eventually there will be a point where the sum becomes 0. But you will not be at 0, 0, 0. You'll be at something like 5, 0, minus 5, which ends up summing to 0. Also, I'll need a minute. I have to put this on charge. But meanwhile, try to think about how we can finish from here. Also, it'll be preferred if like people talk because I'm not looking at chat very often.
We can see
Give
that.
me a minute. I think the plug is reduced. Give me a second. I'll be back.
Okay, sir.
Okay, I'm back. Sorry for that. The charger is over there, so I had to like figure out a way to extend it all the way to here. Yes, people have given the right idea on the chat. So the point is, after your first move, so 1 to 3, when you look at it modular 2, it's just 1 0 1. So after one move, it'll become 0 1 0 because all three have to change. When you're doing this plus 1, like 1 will become 2, which is 0, 0 will become 1, 1 will become 2, which is 0. And after one move again, it'll come back to 1 0 1 modulo 2. But you're saying that the endpoint is 0 0 0. So how does that make any sense? Because we're just like repeating between these two. These are the only two possible modulo 2 configurations. Another interesting question, by the way, for people to think about is if, for example, the things were equal mod 2, or like, for example, if the endpoint was of a similar form, then is it possible? When is it possible? When is it not possible? One simple constraint is that the sum of numbers at the end has to be smaller, as someone mentioned, because the sum of numbers keeps reducing. So what? What is the exact constraint that's needed? But that's not something we'll be discussing right now. But you can, of course, message me on chat if you have any ideas about that. Now, a very similar but different question will be if you have A, B, C, and you go to A minus 1, B minus 1, C plus 2, or a cyclic permutation like A plus 2, B minus 1, C minus 1, or A minus 1, B plus 2, C minus 1. So you're allowed to go to these three starting at, let's say, again, 1, 2, 3. And can you read 0, 0, 0? Sum is invariant. That's, oh, okay. Yeah, that's a joke then. Okay, I'll change it a little bit. Um, can we reach 1, 3, 2? Maybe that's a better question. Yeah. Yeah, so for the starting point, like, I mean, the sum doesn't change when you do this. So 1 to 3, you can definitely not read 0, 0, 0 because 1 plus 2 plus 3 is not 0, 0 plus 0. But yeah, now what do you do? Because now the sum is the same. So sum is, yes, it's a very good invariant, but when the invariant is the same at the start at the end and at the end, it's useless. So now you need to look for another invariant, something else that doesn't change or changes in a somewhat predictable way. And yeah,
I
once
think I
again,
have some idea about it.
okay,
We can look up to mod 3
yes,
because minus.
yes, that's a very good idea. So the idea is that we again want, like last time we wanted minus 1 and 1 to be the same. This time you kind of want minus 1 and plus 2 to be the same, because then all moves will be the same. All moves will just be A minus 1, B minus 1, C minus 1. And if you want to achieve that, you will need plus 2 to be equal to minus 1 in some imaginary world. And that imaginary world is when you look mod 3, because then 2 is the same as minus 1, because 2 minus minus 1 is divided by 3. So if you do look at this modulo 3, now the you always go from like we start at what 1 2 0, and you're always doing -1 plus 2, but that's same as -1, so you're reducing all by -1. So that'll take us to 0 1 2, because 0 minus 1 is -1, which is again 2, and this is 2 0 1. So the ending point should be one of these three, because if you do it again, you'll come back to 1 2 0, which is where we started. So it has to be one of these three. But the one that's given to us is 1 0 2, which is not existent here. And so we have a contradiction. This doesn't work. So this is the basic idea behind invariance. Like you start simple, think of like something like sum that is not changing, but as things happen, it'll be very useful not to think of things randomly, I feel, because a lot of people, intuitively, they just know that, okay, we should do mod 3, right? Like, I mean, it makes sense. But having a concrete sense of how you come up with mod 3 is useful, because there'll be problems where you'll have to use that sort of concrete sense. So, yeah. So what if here too we did not get a contradiction? If we did not, then either you look for another invariant, or perhaps it's possible. Maybe it's possible. Like maybe it's just possible to go from 1 to 3 to 1 3 2. So I think there's always going to be a balance when you're trying problems. There'll be one half of you which will be like, okay, I'm going to try and get an invariant and prove that you cannot do it. But there should also be another half of you which is actively actually trying to reach 1 3 2. Like, maybe try some steps. Like what happens if I go to 3 1 2 by doing +2 here, etc., etc. And sometimes what happens is some people like to prefer with this because it gives them a little bit of a feel of the problem. And then they're more like, if they're not able to reach it after even trying for like 5-10 minutes, then they start feeling that, okay, maybe it's false. Maybe I should look for an invariant. Whereas other people like start by looking for invariants. If they can't find one, maybe it's reachable. Maybe I should try that. So it's always going to be a balance of the two. If you keep trying for one, like it may not be. Can invariants ever prove that a solution exists? No, not directly, no. You will always have to come up with an algorithm to show that you can go from something to something, which is like literally like construct a way. Okay, I mean, there will be some places where you can prove that there is a way, even though you don't actually tell what the way is. But to answer the question, no, an invariant directly cannot tell you that there is a way. It can only tell you that there is no way. So in that sense, it's limited. And that's a limitation we should know. But that doesn't mean it's not useful, for sure. So that's the basic idea behind invariants. Now let's try some slightly trickier problems. Or okay, before we do a little bit of tricky problems, I'll also like to introduce this concept of monovariants. Now, monovariants are quite similar to invariants in some sense. The only difference is that when you say invariant, it's something that doesn't change or changes in a very, very predictable way. Monovariants, you have less control over. All you know is whether they increase or decrease. So, for example, in this scenario where we did that a minus 1, b minus 1, c plus 1, notice that the sum of numbers after each step reduces by 1. So you can say that the sum is a monovariant that always reduces. So why this is useful is that if some quantity always reduces and the quantity is the same at the start at the end. And notice that earlier we didn't want the quantity to be the same, but now we want it to be the same. So in fact, if this is at least a, and we know that it's going down, like a is going reducing, but the final configuration is at least a. That doesn't make any sense unless you were somehow like at equality at each step. Those sorts of constraints come in later. But the basic idea is that if something is reducing, it can't go back up. Like if you've proven that it always reduces, that can also be very useful. So to give an idea of that, I mean, yeah, one basic example is like this same problem. If I'd asked you to go from 1 to 3 to 3, 4, 5. Now you can't. Now, the interesting thing is if you do the same mod 2 trick, which is like +1 is same as -1, you'll actually find out that this is 101 mod 2, and this is also 101 mod 2. So that actually doesn't help you at all. It's an invariant, but it's the same at the start at the end. But what does help you is the sum, because the sum should keep reducing, but here it's increased. So that doesn't make sense. 422, we can go to 000. Yeah, that makes sense because you can reduce things whatever systematically until like you get 333, and then you can get to 222 after a few moves, and then you can get to 111, etc. So that's in general how you would look at constructing an algorithm. Like maybe like try to systematically like keep reducing, and eventually you reach 000. But that's again not the topic. I'll maybe take another class on that. But yeah. So now that we have introduced both, we'll do the first quite tricky question for today. I'll just paste a screenshot. Oops. So yeah, this is a pretty like do monovariants and invariants exist at the same time? Yeah, like in the previous problem, we saw that yes, there was an invariant, but that didn't help us. The monovariant did. And in another problem, maybe the monovariant won't help you, but the invariant would. So, and sometimes you do need to use both. Like sometimes there are cases where like you need to consider both together and then you get a contradiction. Like if the thing is reducing, then you have an invariant. If it doesn't, things like that. We'll not get into too much detail right now. Also, is there any doubt till now in terms of like what a monovariant is or what? I don't know what the source of this problem is. I think this is just like a very well-known problem. I think I've seen it at least like 3-4 different places, but I don't think it's from a contest because it's just like folklore. Like it's been known since whatever. Can you show the question once again? This is the question, like it's on the screen. What is monovariance? Again, monovariance is the sort of concept of a monovariant. Like monovariant is any quantity that always reduces or always increases. And monovariance is like the concept of using a mono. Question not visible. Is that true? Like, can't you see? We place n stones at certain integer points. There's nothing above this.
We can see the question.
Yeah. Okay. Someone has raised that. I think we'll give like a little more time for people to think about the question because first of all, it's like really cool that you've solved it, but just for so that everyone gets a little bit of time to attempt.
If more than two stones are at the corner, then only one stone is placed to the left only, right?
Um,
If
I don't
more than
understand.
two stones are at the corner,
Yeah. So let's say
then
you have something and there are two stones here.
yeah, so we can only place one stone to the right only.
Yeah, that's true.
Oh, okay, it is not necessary that we have to place the stone at the already मतलब अगर कहीं पे पहले से stone था तो वहीं रखना ऐसा जरूरी नहीं.
Yeah. So like you don't control what happens in between. You only control what is the starting point and the ending point, and you're looking for some sort of invariant monovariant, which helps you prove that something like that.
I think I have some idea, but I don't know it works or not. Can I state it?
1 second. And also some ideas in chat. I'll just quickly go through them first. Someone is given the idea of the product being an invariant, monovariant. I'm not very convinced by that. Like, why should the product reduce? And product of what exactly? But okay, before you answer that, also one idea, we take the sum of distances. Then in each move, yes, this is a good idea that the sum like of the origin, like if you like label the points as 0, 1, 2, 3, 4, you're like moving one to the left, one to the right. So the sum of like the indices will just not change. But sadly, that's not very useful because the question is, can the starting and ending point be the same? And so, of course, like an invariant is never going to help you here because the start and end point are literally the same. You have to find a monovariant, something that reduces and in turn creates some sort of contradiction. Yeah, Anudeep, can you please tell a little bit about your product idea because I'm not understanding very clearly.
If we take the positions of the stones to be A1, A2, A3, so, and to AN, we
Okay.
can say that the product will always go down. Because if we
Okay.
suppose,
I see what you mean. Yes. Okay, that's nice. Yeah. Yeah. So also,
Can
yeah,
I say my
now
idea?
Athar, do you also want to give your idea about what we have done? Like we'll go through, there are a lot of different solutions for this.
I was thinking the sum of squares of positions.
Yes, that's also an idea that works. Yes. So
Yes,
we'll
I'm
go through
also
the different.
thinking that.
Sorry.
I am also thinking the sum of squares, but
Yeah, sum of squares is actually a very good idea. Also, I just realized some problem with the product. There might be some issues if your indices become negative at some point, because then it might start like increasing.
we can choose the position of the first stone to be 0.
Yeah, but
So
it
that
can later move to the left, right? Of 0. Like it, I think there should be some way to make this work. Like maybe make them very far away from the origin, but even then you'll have to do some detailing. But okay, first let's actually talk about the squares idea. But also
yeah,
let's not think about it in terms of squares. I want to think about this slightly differently. The idea is going to be that you're going to give each stone gets a weight. So that's cool. Now what does each stone get do with this weight? Now this weight is based on, at what point on the number line the stone is at. So if the stone is currently at position 2, then it gets weight W2. We're still yet to decide what W2 is. It's like just some number. Like you can think of it as f of 2 also, like just some function which takes, like we're not sure what we do. But what we're hoping is that, the sum of weights of all the stones. So at the start, the sum is something, some weight. So summation of these weights. And later on, it's not equal. After a move, the new weights is not equal. In fact, you're hoping that this will be doubtful. Um, Something like that. So how do we achieve something like this? So the interesting thing is that most of these weights will not like change. Like you're not moving most of the stones. You're only moving 2 stones at a time. So if those 2 stones are at index I, then you're removing 2 stones from the ith index. So this side gets reduced by, okay, let's say instead of I, let's just call this k or something. So we're reducing by wk, 2 times wk over here. And then we're increasing by wk plus 1 plus wk minus 1, if this makes sense, because 1 goes here and 1 goes here. So whatever is the weight of stones on this index, whatever is the weight of stones on this index. Does this make sense to people? We're yet to decide what the weight given to each index will be. But we know that whenever you remove two stones from here, like the total sum of weight goes by 2 times WK, but it'll also increase by WK plus 1 plus WK minus 1. So now all you need is like, well, okay, just to make things a little cleaner for us, we'll do this. So sum of weights keeps increasing. It's really the same thing. I think you can do it either way. But the point is that now you just want this quantity to be positive because this is how much it's changing by. So if you can show that this quantity is positive, then you're happy. And the funny thing to notice is that, okay, the weights are in your control. Like, I mean, just define them recursively, saying that WK needs to be what? Greater than 2W, sorry, WK plus 1 needs to be greater than 2WK minus WK minus 1. So, like, let's say I fix my on 0 as 0 and weight on 1 as 1. Then I'll just like keep doing this. Like now weight on 2 will be greater than 2 times 1 minus 0. So greater than 2. So 3. Then so on, etc. But of course, that's a little bit weird. So if you want to think of something cleaner, what you can do is, for example, think of powers of 2. So powers of 2 have this thing. So if you think of WK plus 1 as 2 to the K plus 1, you know necessarily that 2 to the K plus 1 will be more than 2 times 2 to the K minus 2 to the K minus 1, because this is 2 to the K plus 1. So this is just saying 0 is greater than negative number, which is true. So that's one thing. Now you can also think of squares, which is another cool thing, like K plus 1 whole square, which is another weight that you can give things. If you compare this with 2K square minus K minus 2, because you will get something like 2 is greater than, is that what these weights are, it could be power of 2, it could be square, it could be just W, like weight of K, it could be just be K. You don't know what it's going to be. But once you know the inequality it has to satisfy, like you can do basically anything. Like, I mean, you can just define this as like 10 times larger than the previous one. That just works because it's surely larger than 2 times the previous one. So even if you do like 10 or something, that's nice. If you do powers of 100, that's equally valid, etc. Yeah, I understood the product idea from x square changes to x square minus 1. Yes. So the point there was that you have a1, a2, an as the indices. And in a move, you're taking two things which are ai and replacing it with ai minus 1 into ai plus 1, which is ai square minus 1, like strictly lesser than this. But sadly, there might be some problems here which you'll have to handle because sometimes things can become negative, which will kind of reverse the inequality. But
Why
yeah,
negative will reverse the inequality? I did not understand. Because AI
maybe,
squared is always positive.
yeah. Okay, I'm so sorry. My my phone's data ended up dying, and like I'm at CMI currently, so it's a little bit messed up. I'll just restart and we'll continue. Um, yeah, I think the recording is still ongoing. Let me check once.
Yes.
Okay.
Yes.
Yeah, so this product idea is a little bit messy, so I won't get into that. We can discuss it a little bit later. But yeah, I think with the right sort of details, it can work out if you move everything very far away from the origin, because then everything will just stay positive. But the idea I want to leave is this sort of idea of weighting everything. So you give each stone a weight based on where it is. And what these weights are, you decide later based on the inequality. So if you get something like this, where you need to define the k plus 1th weight in terms of the previous ones, now you can just make it much larger. And okay, recursively, if you also want to do it on the other side, so you want to define wk minus 1 in terms of wk, then you can make it much more like negative or something than the previous one. So that's the basic idea. Of course, there are these slick things of, sum of squares, etc. works, but the basic idea behind all of those is you just need something that works, like some weighting. And the most intuitive one for me, I felt, was this binary thing, but a lot of people seem to prefer the squares. Please tell the question again. The question was that, you have a lot of stones, and each time you have at least two stones at some position, you can move one to the left, one to the right. And okay, like you decide to give each stone a weight so that so that the sum of keeps increasing. And if the sum keeps increasing, then
Your
you
voice is echoing.
like go from start point to the same
Your voice
point
is breaking.
again, because I mean you can't, like, the weight has increased, so it can't be the same thing again. And then the question becomes, how do you weight them? Okay, hopefully it should be better now. Maybe I'll also like turn off my camera to like save a little bit of internet. Maybe that would make things a little better. Okay, is there still some sort of echo or like bad breaking net or something
No
like that? Is
sound
it
is
fine?
clear.
No, it's okay now.
Okay, cool. I'm sorry for
Sir,
delay.
I have a question.
Go
Could you
ahead.
please explain the monovariant again? It's a bit unclear.
Yeah, so the monovariant is something we decide later, funnily enough. Like, we don't really care about what it is, we just want to make it exist. So, how we start is that, okay, we know we are going to be looking for a monovariant. Cool. And what sort of monovariant is this? It's like a summation of weights. We're giving each stone a weight based on where it is placed. Like, we have marked the integer points of the number line, and any stone that is on the fourth position will get W4. We don't know what W4 is. It's just some number. We'll decide that later. But what we need so that the sum increases each time is this inequality. Because each time we're removing two stones from the kth position, moving one to the left, one to the right. So we're reducing by Wk 2 times, increasing by Wk plus 1, and increasing by Wk. And all we need is this is positive. So for example, you can make the weight power of 2. You can make it power of 10, in fact, if you want to leave some room to spare. Like, like if Wk plus 1 is 10 times the previous one, Wk, then you know that it's going to be much larger than 2 times Wk minus 1. So if this inequality holds, that is by using power of tens or whatever we did, if that inequality holds, then this summation of weights will keep increasing every time you make this move. And so at this, the question says, is it possible to form a non-zero move? So non-zero means that the weight has reduced at least once. And we want to get back to the same position, which doesn't make a lot of sense because, I mean, the weight has reduced. So you can't get back to the same weight. Does that make sense?
Yeah, it's good.
Okay. So, yeah, that's the basic idea of weighting. Let's do another problem. This one is a reasonably well-known problem. It's 2009 C1.
Excuse me, sir. Sir, I wanted to ask that we made that quantity positive and we defined a function accordingly. So
Yeah.
can we make that quantity negative so that the quantity
Yeah.
the total weight always decreases?
We can do that by, for example, making Wk plus 1 1/10 of Wk. Then you'll get the reverse inequality because,
Yes.
I mean, okay, you'll have to be a little more careful about the details, but basically the point is you can also think about it like reverse your number line, right? Like here all our weights are like increasing. Now if you think of like just flip the entire number line, everything will reverse. So now summation of weights will start increasing, etc. And that will also lead to a solution. So yes, I mean, now you will just need a number which is less than 2Wk minus Wk minus 1. So for example, you can just take like minus 10 times Wk minus 1 or something, because then this is larger, right? Like this inequality would be true, because if you take this to the other side, okay, actually, it's not that easy because now you need to take care of negative things. So maybe it's a little safer to do it this way, but it can be done. I think that instead of multiplying by like minus 10 or something, it's better to do half because then you're not going to run into those situations. Like if you think of 1/2, 1/4, etc. as the weights, I think that should also work. Like then it'll keep increasing instead of keeping reducing. How
Yes,
old are
understood.
you? That's a question for later, but I'm 17. Okay. Um, yeah, let's try this question. This is 2009 C1. Greater than 0, can you explain? Um, we just want the summation of weights to increase. And we know that the delta that happens is this. Like, this is how much it changes by. So if this is greater than 0, that means that it changes by a positive number. So if it changes by a positive number, then it increases. That's all we're saying. Explain the problem. No. You read it for a bit, then I'll explain it after that. Let people try and get better a little at interpretation skills as well. That is also an important skill. I think sometimes in classes like we end up like explaining problems in a lot of like depth, but it's important to build a little bit of that skill also. Okay, someone has given a decent idea, but yeah, that doesn't like. So the idea for reference is that the number of cards doesn't change, which is true, but that doesn't say whether the game is going to end or no, at least not directly. In fact, it might have been better if the number of cards did change, because then if it kept reducing, eventually there would be no cards left, and therefore it has to end. What does legal move here mean? Okay, so I'll explain the problem now. So you have 2009, and in general, okay, you have like n cards, or let's just say 2009. Each of them has a gold side and a black side. Um, Initially, all of them are gold, so I don't have gold color. Okay, I can use this. Like, this is the best I can do. And all of these are like yellow or gold, whatever. And you can choose a block of 50 cards, the leftmost of which is showing gold, and turn all of them over so that each thing that was gold and black is that's it. So you choose some card so that like it's yellow, like you choose some block of 50 cards first of all, so that the leftmost one of them is yellow. So at the start, everything is yellow, so you can do whatever you like. But after that, like all of these cards get flipped, so these would become black, etc. So all of these are now black, the first 50 cards, let's say. So now you can't like if you're picking your next block of cards, it can't start from here because this card is not gold. You have to start at a gold card. So for example, if this card is gold, then I can choose to start from here, etc. And the point is you'll just first instinct is that okay, I mean slowly like all the golds will become black and then you can't do anything because like if there are no golds left, you can't make any move. But the point is that there can be some issues. So for example, let's say that at the start everything is gold, which is what they've told us. And we choose to make second, third to 51st cards. We flip them because I mean this one was yellow, so that's illegal. And we flip them and make all of these red. And then black. And then we flip from the first point. So now these reds have actually again become yellow. So the number of yellows can again increase. So it's not as clean as just the number of golds is reducing, but we'll have to do something slightly small. Someone has given the right idea here. Yes, I think the game will, yeah, that's a problem. Yeah. There are very few states, right? One with all black, two gold, two so on. No, but there are 2009 cards, not 50. Like you choose 50 cards in a move. So are we going to prove that the last 50 cards will not have black sides at some point? No, that's not what we're proving. We'll prove that eventually all the cards except possibly the last 49 will all become black. Because that's the only point where you can't make a move. Like if any of these cards is yellow, then you can just choose this and operate on it. So also like notice that there are two plays here that's more related to part B, which we'll not be doing today, even though that's also a cool problem. For our reference, this is only like it's 1%. Vice versa, meaning vice versa just means that, for example, like gold shows black, black shows gold. So if a card was showing gold, it becomes black. Card was showing black, it becomes gold. Someone has given the right idea on chat, yes, that you are going to look at it in binary. But that's not the way I would like to actually think about this. Because even though that works and it's obviously a realistic solution, I think there's a very clear way you want to think about things. And I don't think that's the way. So the way I like to think about things here is you give like again number all of these things. So let's say I number from the right. So 1, 2, sorry, 3, uh, sorry, 3, 4, all the way till 2000. And I give each card a weight. So weight 2009, weight 2008, dot, 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 and then like weight 1. And now I'm going to do very similar stuff. So I'm giving them weights. And I want to show that this ends. So I want to show eventually, like I like the weights will keep reducing, but also weights will stay positive or something. So it can't go on forever because you can't keep reducing something by an integer amount while keeping it a positive integer. So like you start at 5, but you're always greater equals 0 and you're reducing. That means it must end. So like 5, 4, 3, 2. Eventually you'll have to reach 0. And then you're stuck. So that's the basic idea. And now the interesting thing we'll do is that we'll count the weight of all of the yellow cards or the gold cards. Like the black cards we'll ignore, but we'll add up sum of all weights of gold cards. Now this is a question like why did we think of this? Now, I mean, the cleanest answer I can give to that is that like I mean, you have two types of states. For one of them, you should probably think of adding the weight. For the other, you should think of not adding it. You could choose to, I mean, take sum of all weights of black cards, and I think even that should work. But I think this is just a little bit cleaner, so I'm going with this.
It's like the binary one because we are adding the ones with some 2 to the power on it.
Yes. So again, binary is the right idea, and we will reach it eventually, and then we will see how it all comes into place. But I want to just lead towards it rather than like giving it off strictly. So let's think of the weight, right? You have like what happens when you make a move. There is, let's say you make a move from k plus 1 till k plus 49, 50 cards these are, or I'll just say k plus 1 to k plus 50. So now you know that this card is yellow. So you know that you have definitely reduced by WK plus 50. But it's possible that, you know, some of these cards were black and now they're yellow. So you've increased by WT. You might have increased by WK plus 1, etc. So what is the total change, net change that has happened? You've got a negative of WK plus 50. And the other stuff we're not very sure of. So let's just take the worst possible scenario, which is that, like, okay, we're trying to reduce the sum of weights. So the worst scenario is where everything is against us and everything is trying to increase the sum of weights. So all of these are like positive. They're trying to balance out this guy. But even in that scenario, like we can just choose WK plus 50, which is saying that like leftmost weight or whatever is just much, much bigger than the sum of all the previous weights. Like if for example, you define your first weight as 1, like first few weights you can define however, and then when you come to the 50th weight, you just define this as the sum of all these numbers plus 1. And then you define this one as the sum of all these numbers plus 1, etc. So the point is that this weight thing is going to grow very fast. And therefore, this weight will always outgrow whatever happens here. Whether it increases, reduces, it doesn't matter because this one is what's going to decide the change in sign, whether it's increased or reduced. And again, that's the main idea. So now you can just choose, I mean, you can recursively define it. And the clean way of doing it again is to think of powers of 2. Because powers of 2 have this nice property that power of like 2 to the n is more than all the previous powers of 2. Like 2 to the n is greater than 2 to the n minus 1 plus 2 to the n minus 2, all the way till 1. Because this quantity is just equal to 2 to the n minus 1. So that's how you can sort of motivate this idea of coming to powers of 2. And when you come to powers of 2, you can also think of this sort of binary idea. Now, that's actually another very interesting thing you should probably think about, which is that when you have two possible scenarios like gold or black, it's useful to think of it in terms of 0 and 1, because it's also just easier. Like you don't need to color things like I was, but also it sometimes helps. So when you do that, like you had some 1 1 0 1 0 0 sequence, and you chose some sequence which starts with a 1, assuming that 1 is gold, and that becomes 0 and other things change. But because like if you write this number in binary, which is what people were suggesting, this number has to have reduced because the leftmost one has become a 0. And whatever happens to the right of that is irrelevant because like again, like 2 to the n is going to be bigger than, it's the same idea. 2 to the n is bigger than the sum of all of the previous. So take a bit. Is it cracking for someone else? Like, I mean, I saw Ashutosh said that, but like for others, is it okay?
We can hear you now, but your voice is before cracking.
Yes, sir.
Okay. Yeah, I think, okay, hopefully it's like, take a moment to like think about this. Like you can write this in binary, you can do this in terms of powers of just making this like so much bigger. But the idea is the same. You want to make the weights increase. You want to find a monovariant. Does that make sense to people? If there's like a doubt, we can talk about this again, because this is the example. If you understand this, then like you're clear with full invariants and monovariants.
Could you explain the whole solution, please, again?
Okay. So to start off with the question, like you are choosing a block of 50 things, the leftmost has to be gold, and if make all of them black now, but these ones,
So your
so
voice
like
is
the process
breaking again.
there's no um got my thing a little closer. Can people hear?
Yeah,
Yes,
now
now
it's
it is
clear.
clear.
Yeah, now we can
Okay,
hear.
cool. Cool. So you have, yeah, so we were here. So the point is that again, we're going to give each position a weight. Like this is the first card, this is the 2009 card. Each card will get a weight. We'll decide what those weights are later. But we'll do it so that the sum of all weights of the gold cards increases. Now, this is a bit of a random quantity to consider, but like two ways of thinking about it is that, you can't consider the sum of all weights because that just never changes. So you're going to consider some like either sum of all black cards or sum of all gold cards. Both of them work. It's just like I chose to do this one. Um, and when you do that, the K plus 50th card has gone from gold to black. So we know that it stopped mattering to us because we were only considering the gold cards coming. So we have to subtract WK plus 50. And the others we're not sure about. Those are 49 other cards. But what we do know about them is that if we make this card a lot bigger than the previous weights, if we make this weight a lot bigger than the previous weights, then we can make it so that even if all of these go from black to gold, then also the sum of weights reduces. So we're hoping to show that reduces. And for that, the worst, like we're already getting a negative thing. So the worst case is that everything else is positive for us. Like everything else is trying to show us down. But even in that, we can make WK plus 50 so big that not all of these things combined can also show it down. Like WK plus 50 is just going to be much larger. And like the cleanest way of doing that is using powers of 2, because you know that 2 to the n is bigger than the sum of all previous things. But you don't have to do that. That's something I want to stress. Like you can literally just define WK plus 50 as like just some number which is like 10 times the sum of the previous numbers. Like that's it. Like then it's going to definitely keep reducing, and that works. Now, most people like to think about this in the binary way, which I think is a lot more slicker and cool. But this is a lot more intuitive, I would say. But okay, to be fair, the first time I saw the question, I saw it like this. But yeah, the idea with this binary solution is that whenever you have two states, gold and black, you can think of them as 0 and 1 and write them in terms of these sequences. So like gold, black becomes like 1, 0, 1, 0, etc. And then you're basically like going to choose 50 cards so that the leftmost is a gold, that is a 1. and flip them. But when you flip them, the point is that the leftmost binary digit matters so much more than the others. Like, for example, if you think of this in base 10, if that makes more sense to you. If I change this 2 to a 3, so I make it 1300 something. Even if I make these 0, like 1300 is still going to be bigger than 1234, no matter like what I do with these two digits. The same way here, if I make this 1 a 0, then no matter what I do with these digits, the number has to reduce. Because this number is just bigger, like this digit is bigger than this digit and the previous ones are the same. So that's the idea there, which is that the binary number will keep reducing. But we're not done actually in either of these solutions. So here's the question, like what did we actually prove? We showed that the sum of weights keeps reducing. But the interesting thing now is that there are only finitely many possible values of this sum of weights. Because, like it's possible that the 7th and the 11th cards are gold, rest are not, etc., etc. Like there are only so many values that this sum of weights can take. But if it keeps reducing forever, like infinitely many times, then it must take infinitely many values, which is not possible. Like similarly, in this proof, you will say that, eventually your binary number will become 0, 0, 0, 0. And like after that, you can't reduce it further. So that's the idea there. Could you please explain how this contributes to the final solution? Yeah, like I think I did that now, but if it's still unclear, like the point is that the question was, does the game end? And we've shown that if this keeps reducing, but also another way of thinking about it is like, let's say all these weights we define to be positive, then the sum has to be positive even at the end. But if you're keeping on reducing it forever, 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 and also it's an integer every time, like we've all of these weights we can define to be integers. Like again, it's all in our hands. Then
It
yeah,
must go to 0.
sorry.
Then it must go to 0 because it's keep decreasing every time.
Exactly. It has to go to 0, and at that point, like, I mean, there's nothing left that can happen. Does that make sense? Yeah, also, yeah, about the book, I think I mentioned this at the start, but some of you weren't there. Like, yes, it shows unavailable right now on Amazon. It'll probably be fixed, so don't worry. It will be available in the future. Okay. I think we've covered most of the things I had planned to cover. There are a couple of more questions that I can give you people for your own practice. Although I can also just put those in the preset, so I guess I'll do that. Yeah, I think we ended up finishing a little early than I expected, but I think that's okay. Before I'll stop recording, but if people have any questions, they can like